All right, yeah, thank you very much. I'm very happy to be here to have the chance to present this work, which will kind of go in opposite order. We'll start by discussing some applications to L functions, why we care about those applications, and where we are in that status. And then we'll talk about some of the techniques that have gone into these applications, such as the orbit method and microlocal analysis. So, okay, many of the speakers have already used the line that we're at a number theory conference where maybe we don't need to say what L functions are, but okay, we'll start from the beginning anyway. So of course there's the zeta function of Riemann, which I stole a picture from Wikipedia of right here. And there are many open problems in mathematics concerning this function. So I guess the start of the story is the prime number theorem, which predicts how the number of primes grow, and it predicts that if you take the prime staircase function, which counts how many primes there are up to a given bound, and you zoom out, this kind of looks like this smooth function just given by a simple ratio. And so this, in the proof that developed, turned out to be equivalent to a property of the zeta function concerning where its zeros locate. And there are open questions concerning the zeta function, which predict finer control over the zeros. So there's the Riemann hypothesis, which predicts that the zeros lie on the critical line pictured here, which corresponds to a stronger form of the prime number theorem. And then there's the Lindelof hypothesis, which predicts that if you look at the zeta function on the critical line, so when it's not busy vanishing, which you see when the peaks go down here, this is a graph of its absolute value, it predicts that it grows very slowly. So you can see from this picture that it's only grown up to size about 3 when we've extended the imaginary part up to a size about 50. So it predicts that quantitatively it grows slower than any power of t. And this is known to be a consequence of the Riemann hypothesis, but it's one of these inaccessible problems that just kind of motivates us. So there's a more accessible way to quantify progress towards that problem called subconvexity. So what's pictured here is upper bounds for what's called the growth exponent of zeta, which is indicated here, quantifies how fast it grows for a given real part as the imaginary part of the argument goes off to infinity. So it asks, what exponent can you put in t so that you have an upper bound like this? And there's this blue line that follows from kind of general complex analytic soft features called the convexity bound. And so it's obtained by interpolating in a convex fashion between the kind of known behavior when the real part is bigger than 1 coming from the definition and the functional equation which tells you how to relate the values at s and 1 minus s. So that's the blue line. If you believe the Lindelof hypothesis, then you can put a dot at 1/2, which says that it grows slower than any power there. That's the green line that you get by interpolating. And then the red line is what's called subconvexity. It means proving anything better than the blue line. So any exponent smaller, for example, at 1/2, although any other point would also do, interpolates to a smaller bound in the whole critical strip. So for the zeta function, this is a theorem that goes back to Weil, Hardy, Littlewood, and Landau. So they showed that, you can bound the growth exponent by a little bit less than 1/4. That was the kind of trivial bound represented by the blue line. And so they obtained this exponent of 1/6. And I think they were motivated just by kind of trying to intrinsically understand the zeta function. There's been a century or so of progress chipping that exponent down, with the record being what's written here, established just a few years ago. But okay, beyond establishing improvements to a bound like this, another way one can try to understand things better is to try to establish bounds like this more generally. So I guess the generalizations of the zeta function, as I've already come up in some talks today, are the so-called L functions, which always have a shape kind of like what's written here. They involve a product over the primes, but with some additional factors occurring in the denominators. So a kind of uninteresting or less interesting example is a power of the zeta function, but then there are more interesting examples coming from other automorphic forms. So There's a long history that I'm not intending for us to read here, but just, as you see, there are many names and many dates attached to various L functions that have been introduced over the centuries to quantify other aspects of how the primes behave, such as how they look in arithmetic progressions, or maybe how they look with respect to splitting conditions in number fields. But okay, conjecturally, all of these definitions are special cases of what are called standard L functions, which come from automorphic forms on GLN. So an example being this nth power of zeta, which comes from an Eisenstein series, which is a particularly explicit automorphic form. But then there are less explicit L functions that come from less explicit automorphic forms. So just to give one very explicit example arising in recent work, so there's this, there's this old example of a modular form going back to Riemann, defined by this series expansion. And there's a theorem of Deligne that says that each of these numbers can be written in terms of some angle that's called theta p. And then there's a relatively recent result of Newton and Thorne showing that if you form the L function written like so it's attached in a natural way to the symmetric power of these angles, this turns out to be a standard L function of degree n+1, meaning that you can define it using an automorphic form on GLn+1. So this would be an actual, completely explicit example of the kinds of objects we're talking about. So yeah, the talk will be kind of centered around the problem of estimating these things. We should maybe say a little bit about why we have historically cared. So there's the intrinsic interest, which I think of as going back to Hardy and Littlewood and company. And then there's also more recently some applications that came about in the 80s and 90s. So maybe the first class of applications concerned how sums of squares distribute themselves when you fix the value they take. So what you see here was I picked a year fairly close to 2025 that satisfied some local conditions, and I wrote down all of the ways to write that number as a sum of 3 squares and plotted them on a rescaled sphere. And so the question is, do these things equidistribute, or do they behave more badly as the number n goes to infinity? And this is a question that was understood in works of Ivani H. Duke and many others, and it eventually boiled down to a bound for an L function. And the other kind of canonical example is this story of quantum equidistribution, which asks, how do eigenfunctions of the Laplacian of large eigenvalue behave as their eigenvalue increases? So these are some pictures due to Alex Barnett and Holger 10 that show kind of the densities of these eigenfunctions. And so it's predicted in this quantum equidistribution conjecture of Rudlick and Sarnak that these actually tend towards the uniform measure as the eigenvalue increases. So meaning you can kind of see in these pictures some kind of erratic behavior that looks like it might represent a density concentrating on a geodesic, but actually that doesn't kind of happen in the limit. They all end up being uniform. This is a problem that was resolved in a qualitative form by Lindenstrass, but in its kind of original quantitative form remains open. And it would in any event follow from bounds for a suitable family of L functions of degree 8, which are still open today. So that's one of the kind of motivating problems in the subject still. So, okay, one fairly recent result that kind of motivated some of the technology that I'll talk about in the talk is the problem of just bounding a standard L function as its argument varies. So if you, for example, fix an automorphic form pi and you vary the argument t, there's again a convexity bound which looks like the nth power of the convexity bound for the zeta function. And there's a long history of work on cases of this problem, I guess quantitatively mostly for n up to 3. So a few years ago I at least put on the archive a result establishing this for general n, saving a very small exponent as you see here. And yeah, it's given as kind of a result in the third of a series of papers that I'll talk a little bit more about in the talk. And okay, just to put this in kind of a little bit of a broader perspective, since this is a number theory conference, this is kind of not at all the end of the story as far as subconvexity even for GLN. So in a bit more detail, so if we take an L function on GLN, which we've called L of pi s, we can attach to it some n tuple of complex numbers that I'll call lambda 1 through lambda n, that are the numbers that show up in the functional equation. So they're the numbers you have to shift the gamma factors by so that the functional equation has a clean form as you vary s and replace it with 1 minus s. So using those, there's a definition of an analytic conductor that is basically the product of the sizes of these parameters shifted by the argument t. And there's a general upper bound due to Ivanich for GL2 and then Molteni more generally that says you can bound any L function uniformly as the automorphic form pi itself varies by this conductor to roughly the quarter. So all of the applications I discussed a few slides ago concerning how points distribute on spheres or quantum uniqueridicity would follow from an estimate like this in complete generality if you could improve the exponent by a small amount. But what do we really know? So for instance, just focusing on the case when the level is 1, which is what you get from automorphic forms in GLNZ. Okay, my general results said that if you assume that each of the numbers that go into the conductor are roughly of the same size, and so one way to quantify that is to bound them from above and below by multiples of a parameter, then you can get a subconvex bound. And of course, this number just doesn't matter so much. It gets a little bit better every year that I present this, but it's not going to tend to infinity with t anytime soon, unfortunately. So relaxing that assumption is kind of a very important open problem. So getting rid of this lower bound here, just requiring that, requiring nothing. That's kind of the case that will be relevant for this application to quantum uniqueridicity, and so it's one of the main open problems in the subject still. Okay, so yeah, maybe I'll just quickly pause for questions because I've kind of summarized a few results and I'm about to transition a little bit. Cool. All right, so I wanted to say a little bit about things that have come out in the past couple of years concerning kind of other variants of this problem. So for instance, you can ask about level aspect variants, which, okay, have a long history that I'll kind of recall a bit ahistorically here. So the first result that I stated a couple slides ago, you could summarize as saying that you have subconvexity for twists of any L function by absolute value to the IT. So twisting by that absolute value is kind of another way of saying that you vary the argument 1/2 plus IT. But you could ask more generally, how about twisting by other Dirichlet characters? So say chi, and so a Dirichlet character can be ramified in any place in the rational numbers. So it could be ramified in infinity, and you could have its ramification be some number t. That's the case we've considered here. You could alternatively have it be ramified just at a prime 2, and then let the power of that prime describing its conductor go to infinity. Or at an opposite extreme, you could have it be ramified just at some varying prime p and have that prime be its conductor exactly. So there's some kind of vertical aspect that's treated here. There's a related vertical aspect at any given fixed prime that is kind of a very similar story to what happens here. I'll come back to that in a bit. And then there's a purely horizontal aspect where you say, let the conductor of chi be a prime that's tending off to infinity. And those kind of represent different directions in which you can generalize this question. So what we know now in some work with me and Yuki Hu, it's come on the archive in the past couple of years. So there was one paper a couple of years ago and another paper earlier this year, is that we can do this provided that the conductor of the Dirichlet character is a square. Okay, we could also do it if it were a power of a fixed prime. That's kind of still fairly close to the earlier result. So the key new case that we were able to work out is when the conductor is, for instance, the square of a prime number, where the prime number is varying and tending off to infinity. So Yeah, so that took some work to understand. But we've left open the case where the conductor is exactly a prime number. That is still kind of an open question. So there's some beautiful results of Rita Bradamunci, and then myself and Holowinski, and then Prahlad Sharma in the case of GL3. And there's a huge number of results for GL1 and GL2. But for instance, for GL4, it's still an open problem to understand the character twists of a fixed L function if the conductor is a prime number. And maybe there's a reason to actually care about such character twists besides the intrinsic interest of estimating L functions for their own sake. So there's a formula of Lapid and Mao that says that under some conditions, the values that you get by twisting by a quadratic Dirichlet character are related to some metaplectic Fourier coefficients, which in turn you could imagine might say something about representations by quadratic forms. So in the case where n is 1, this is a very classical story. That's the whole Duke Ivaniev story that I presented earlier involving sums of 3 squares. So there's kind of a potential story that one could tell in higher degree here that has not yet been told, where both the elaboration of the story and the estimates that would power it are kind of open questions. But it might involve, for example, understanding, let's say for a degree 5 quadratic form that's maybe indefinite, understanding the distribution of lines consisting of entirely or spanned by integral elements, let's say. So there's some kind of fancier versions of the Duke-type theorem that might be amenable to estimates for these things. And then just to give a bit more history, so I mean, these are actually special cases of results for GLN plus 1 times GLN obtained by specializing to the case where the factor on the smaller group is an Eisenstein series, so that the L function is just the nth power of the L function on the bigger group. And so in this more general setting, where maybe you also allow yourself to replace GLN with a compact quotient variant defined using unitary groups. So there's some work of Simon Marshall establishing bounds, assuming some additional conditions, and then I had an earlier paper also establishing bounds without those conditions. And then there's also been some work of Liang Yang more recently, and maybe also some ongoing work by Liang Yang, generalizing these things further. So there's still some ongoing work treating kind of the general Rankin-Selberg case. Okay, and with that kind of survey of results, I wanted to say a little bit now about the kind of general method that we use for studying these things. And so many of us, if we've either taken or taught a course on complex analysis where we prove the basic properties of the Riemann zeta function, we've probably seen the proof where you take the theta function and you take its Mellin transform and use that to represent the zeta function. So I guess what you actually get is the multiple of the zeta function by the gamma function. And this is a simple case of the kind of general paradigm that the main tool for actually proving anything about L functions is the theory of integral representations using automorphic forms. So a couple of things one can point to already in this example is that it's very convenient that the gamma function does not vanish at any point, because this, for example, allows you to determine the poles of the zeta function just in terms of the poles of this integral over here. You won't kind of get any additional poles for zeta by inverting this relation and encountering a zero of the gamma function. So, okay, more generally, you have integral representations attached to automorphic forms, which, okay, this is kind of my, very brief summary definition of automorphic forms for a general audience. It's that they're functions on quotients like this that behave like eigenfunctions in kind of every conceivable sense you could imagine. So they should be, as we know, under the Heck operators and also under all of the differential operators, they should be eigenfunctions. And so these are organized into representations, which are, if you like, they're kind of the common eigenspaces for all of the interesting operators we can write down. So I'll call an automorphic form V, and I'll call up the representation that it generates pi. So these are typically infinite dimensional spaces of automorphic forms. And there's a group action by GLNR translating on the right that gives this space some rich structure. So when we want to write down integral representations of automorphic forms in higher rank, these usually involve, or okay, at least in these examples, they involve a pair of groups. So say GLN plus 1 and GLN. So okay, it's a bit of notation here. So I'm going to use, just for the time being, I'll use pi for the representation on the big group, sigma for the representation on the smaller group, and then V and U for the automorphic forms in the two representations. So there's a general relation that is, you can think of as kind of analogous to this identity involving the zeta function and the Jacobi theta function that says that if you restrict the automorphic form on the bigger group and integrate it against the automorphic form on the smaller group, you'll get the L function for their Rankin-Selper convolution times something that I just call a special function that depends upon the two vectors V and U. So in the example from a couple slides ago, this special function was the gamma function. And so more generally, it's some integral of Whittaker functions attached to V and U. And its behavior kind of determines, to a large extent, what you can say about an L function using an integral representation like this. So for instance, if you're interested in proving that an L function is holomorphic to a large degree, knowing that the special function does not vanish, much like the gamma function doesn't vanish, is a very useful input. And if on the other hand, you're doing analysis where you want to bound an L function, say from above, you want kind of a quantitative variant of non-vanishing for the special function. You'd like to know that the special function is quantitatively quite large. So for instance, the gamma function is a bad example because, as you might know, the gamma function, when you vary its vertical argument, exponentially decays. So that would kind of not qualify as being quantitatively non-zero. So there's a great deal of art in using identities like this to study L functions. So it kind of goes back to so many people. So I would say in most recent decades, so Bernstein and Reznikov wrote a series of influential papers, and then Michel and Venkatesh also kind of taught us all how to systematically exploit identities like this to bound L functions. So the theorems that I described earlier kind of all used an integral representation a bit like this, combined with some study of the special function and some rather judicious choice of the vectors, the automorphic forms V and U in their representations, together with some analysis and some estimates for this integral of automorphic forms, and combined like an upper bound for the left-hand side with a lower bound for the special function to get a bound on the L function. So, yeah, so I guess what I'll kind of proceed to now is, like, I won't really have time to discuss in great detail what goes into estimating integrals like this. I'll give some impressionistic idea, but I'll at least be able to describe the language that we developed for thinking about these special functions and also thinking about how to cook up good automorphic forms for the purpose of having the desired behavior for these special functions. So the question is, how can we choose good vectors V and U in general rank, so outside of maybe the GL2, GL1 case where things are more explicit, so that this relation behaves usefully? But okay, maybe I'll again pause for questions just because we're about to transition. All right, so we'll say a little bit about what we mean by the orbit method. So in a nutshell, this is a heuristic for understanding representations of a given Lie group G, so for instance GLNR, in terms of more concrete data. So the data consists of what are called coadjoint orbits, which are just orbits for the action of G on the dual of its Lie algebra under the natural action. I'll give some examples in a second. And so the idea is that there should be something like an approximate bijection between irreducible representations of a group and the coadjoint orbits for that group. So we'll call pi a representation and O pi its coadjoint orbit. And of course, it shouldn't be just a completely random bijection. It should be compatible with the natural sorts of things you'd like to do on representations and also on cogent orbits. So an example of something you like to do in representations is you like to form characters. So if we have a representation pi, we can form its character chi pi, which says the trace of the action of the representation. And so there's a formula established in various settings that says that the character of a representation can be read off up to some simple Jacobian factor as a Fourier transform of a certain natural measure on the cogent orbit. So just to give a simple example of what this formula specializes to, if you evaluate the identity, then the character gives the trace of the identity map, which is the dimension, and this Fourier integral collapses to just the volume of the cogent orbit. So there's some identity between dimensions and volumes that we'll come back to in a bit. So that's one example of what kind of pins down this heuristic bijection. And to give kind of a concrete setting in which it's known to hold, so if you take the group SO3, where you can think of both its Lie algebra and the dual as free space with the natural rotation action, so then the cogent orbits turn out to be the spheres. So there's the degenerate sphere of radius 0, and then all the other spheres pictured here. And on the other hand, the irreducible representations are classified by their highest weight, which is some integer, non-negative integer t. And it turns out that the character formula holds if you take the orbit attached to a given representation to be the sphere whose radius is 1/2 more than the parameter of that representation. So, okay, ignoring the fact that not every radius arises as 1/2 more than an integer, this is indeed something like an approximate bijection. And if you're doing analytic number theory where you tend to average over a bunch of things and kind of blur your vision out, then this is kind of as good as an actual bijection, because you're not going to see the difference between sampling a function on half integers and on the whole real line. To give another example that's kind of relevant for classical modular forms, so for the group PGL2R, there are now kind of two natural classes of cogent orbits. There are the 1- and 2-sheeted hyperboloids that are pictured up here. And on the other hand, if you look at most of the irreducible representations, let's say the tempered ones, they also fall into two classes. So there are the principal series, which are naturally attached to one class of cogent orbit, and then the discrete series that are naturally attached to another. And you again see that this isn't quite bijective, either because not everything is half an integer, or because you lose the parameter epsilon. But okay, besides that, it's again a fairly faithful bijection. And you can read off a lot of things about classical modular forms and the asymptotics of their special functions from this picture. So just to give a teaser, if you're familiar with the weight structure on the holomorphic discrete series representations that you generate from a classical holomorphic modular form, you can read that off from the vertical extent of this picture here. So the fact that this 2-sheeted hyperboloid is kind of beginning at some height k and goes up, and then begins again at some height negative k and goes down, that's kind of a reflection of the weight structure on these representations. But okay, there are many other such analytic features that you can see in our papers developed from this perspective. So now what do we mean by microlocal analysis? So in its classical incarnation, it's the art of taking a function, for instance, on Euclidean space, and decomposing it into pieces that are localized in position and frequency. And a good example of that is either, okay, what I'm saying right now, or if I were singing, it would be like taking my raw audio and decomposing it into musical notes that kind of indicate, in a position localized sense, what the pitch is. And there's a classical way to implement this rigorously using pseudo-differential operators that I won't go into any further, but it basically gives a way of taking an arbitrary function on something like the musical staff and modifying the volume attached to each note by the value that that function takes at the coordinates attached to the note. So that's what this relation here says. So there's a very natural analog of microlocal analysis in the setting of a representation of a Lie group, which again consists of taking an arbitrary vector. A vector you should think of as now being like a waveform describing some audio and decomposing that into pieces. So the pieces I'll call V tau, which you should think of as something like individual musical notes that are now attached to points tau in the analog of the musical staff, which here will be the coadjuvant orbit. So the coadjuvant orbit kind of plays the role of a phase space for understanding this representation microlocally. And then they should be localized in the suitable sense. So, I mean, here's a picture indicating one heuristic consequence of this philosophy of the orbit method and microlocal analysis. So, I mean, you might remember this identity that said that the dimension of a representation coincided with the volume of the coadjuvant orbit. This is kind of a categorification, if you'd like, of that identity, where you say, rather than compute the volume of this, let's break this coadjuvant orbit up into pieces of volume 1, where each piece is concentrated near some given point. So, you know, think of each of these pieces as being something like one of the triangular patches on this soccer ball, so to speak. So heuristically, these should correspond to ways to decompose the representation into an orthonormal basis, where the basis elements I'll call V tau. So these V tau should somehow correspond to these partition elements P tau. And for instance, one way to make that a little bit precise is you could say that if you look at the action of small group elements on V tau, you should be able to read that off in a natural way from P tau. And so because P tau is a region in the dual Lie algebra, there's a natural way you can attach to it a function kind of in a neighborhood of the identity on the group that'll describe the eigenvalue for that action. So that's kind of like reflecting the tone of the note that is attached to an element on the staff. So okay, we have this approximate, or at least heuristic, bijection between partitions like this, bases like this. We call the vectors that arise here localized at the corresponding partition element. And I'm not going to display it, but we have an analog of the theory of pseudodifferential operators that lets you basically work out arguments as if you had a heuristic picture like this in mind, and then apply a bunch of black box machinery to convert those nice heuristic geometric arguments into rigorous proofs. So we have some collection of, a dozen or so theorems in our papers that kind of give the machinery for making that sort of conversion. And what kind of thing would you actually want to do with these localized vectors that we can construct in this way? So one thing you might want to do is you might want to study restriction problems for representations. So if you take, for instance, the group GLN plus 1 and the group GLN, so H being a subgroup of G, so this is an example of what's called a strong Gelfand pair, which means that it behaves very nicely when you restrict representations from the big group to the small group. So for instance, everything I'm saying here would work also for compact unitary groups. And the assertion there is that when you restrict a representation of the big group, it decomposes as a direct, sum in that case, and more generally a direct integral of representations of the smaller group, which each occur with multiplicity at most 1. So there's kind of a canonical way you can think of each of them appearing in this picture. And what this means very concretely is that you can write down an integral formula for the, just a second, I'm trying to get this. An integral formula for the size of this projection, the size of the norm of the vector in terms of the sizes of its projections onto each of these constituents sigma. So a simple example of this would be like taking a vector in a representation of SO3, decomposing it into SO2 types, and then writing the norm as the sum of the squares of the norms of those constituents. So the relevance of this picture to what we were talking about earlier is that these projection norms turn out to be essentially the special functions that I alluded to very briefly in the discussion of L functions and their integral representations. So This whole problem of producing vectors for which the special functions are, for instance, non-zero, and more precisely quantitatively kind of large, boils down to understanding something about these projection norms in an abstract setting. So if you have a good handle over how to produce vectors and estimate the projection norms, you're at least in a good position to produce useful integral representations for L functions that are eventually well suited for their estimation. So to give some flavor for like how one can analyze these using the philosophy described earlier, so we should first ask, what does the orbit method suggest about restricting or decomposing a representation into irreducibles? It says that this should correspond roughly to taking the cogent orbit for it and disintegrating it under the projection of dually algebras into intersections with preimages of cogent orbits for the smaller group. So I've indicated a couple examples of what this looks like in these two pictures here for the two examples of groups. So SO3 on the left and PGL2R or SO21 on the right. So here the sphere is the cogent orbit O pi, and the equatorial strips are their intersections with preimages of orbits from SO2. So we're taking a sphere and we're kind of slicing it into pancakes, so to speak. And similarly over here, you have an analogous picture, I guess, for the one-sheet hyperboloid, where we're, again, splitting it up into hyperbolas. And I mean, maybe one thing to notice about this picture is that there are some regions where things behave badly. So at the north and south poles of the sphere, the equatorial strips collapse into points. And also, there's kind of a pinch point here where these hyperbolas degenerate into an intersection of two lines where there's again kind of like a point and then its complement that behave a bit, differently than a generic hyperbola would. So those play a special role in our analysis and in many other parts of the subject. So they correspond to this feature called conductor dropping, which is kind of the complement of the uniform growth condition described earlier. But okay, what can we then say about projection norms? So we prove, for example, under some assumptions, so in particular avoiding these bad points, like the poles of the sphere and the crosses, we prove that you can estimate these projection norms by just taking the volume of the partition element attached to a localized vector and intersecting that with this fiber of the cogent orbit and computing the volume. So there's a natural volume measure on these in general, coming from the fact that they turn out to be, under the action of the group H, they're just kind of isomorphic to H. So, okay, this is a very explicit result that, for instance, if we want to make a vector that has a big projection norm, we just choose a triangle over here that intersects the equator. And then we can easily estimate how much time the equator spends in one of those triangles. And that then tells us what the size is. So it collapses what kind of formally in the literature had been rather complicated estimates involving 12 variable integrals of Bessel functions to just a kind of simple geometric picture that okay, you can picture very well on low rank, but it generalizes to higher rank quite seamlessly. And just to give a little sample of what one can then do globally with this sort of input. So this is kind of what happened in my paper with Akshay Venkatesh. So we'll go back to this integral representation, just copying from the slide earlier, where we had pi and sigma, automorphic representations of GL n+1 and n. We had v and u as automorphic forms in them, and we had this identity expressing an L function as some integral times a special function. So if we apply Parseval to an identity like this, so taking v, restricting it, and then taking its L2 norm, this should be something like the sum, or maybe better, the integral over all sigma of the L function times, so I've just written ... depending upon v, but what it is you just take this expression above here, the special function, and you take the sum of its squares over all vectors u in a basis for sigma. So it's some explicit combination of the special functions. And so, I mean, okay, this is an example of the sort of thing we can do. So let's say we want to take maybe not just one microlocalized vector, v tau, but maybe a family of them attached to a subset E of the cogent orbit. So I'll use brackets E to denote the sum of the squares of the vectors obtained from that family. So then that sum of squares, well, okay, we prove using this result from the previous slide that when you integrate that over this smaller group, GLN, you get a weighted moment of L functions times some volumes. So it gives a kind of robust way to produce weighted moments of L functions in terms of integrals of automorphic forms whose symmetry properties we understand in a very precise sense. And so it's kind of only getting the game started as far as understanding these moments, but it's a good first move, and the left-hand side has a lot of structure coming from the way that this function brackets E is constructed that can then be eventually exploited in some cases to actually estimate this left-hand side. So I'll indicate in this little bibliography section how we estimated those in the case of our paper. So, okay, we're proving bounds for a family of L functions. So in this generality, you should think of these L functions as like the squares of the L functions on the previous slide. So we're using the fact that if you take a fixed representation and you think of its cogent orbit as having been zoomed out a great extent, which is what happens when you do kind of high frequency analysis, you're looking at parts higher and higher up in the cogent orbit where it looks more and more like that, then the orbit kind of looks more and more like the nil cone, which is the set of, for example, nilpotent elements in GLN or in n by n matrices. And so it turns out, for reasons that we don't really have time to go into, that these vectors, and more precisely their squares, when tau is close to the nil cone, they acquire a great deal of invariance under the part of the group that doesn't move tau, so the stabilizer of tau. So this is a unipotent group, and there are well-developed techniques in homogeneous dynamics for converting unipotent invariance into equidistribution. So with a bit of Ratner theory, we're able to actually evaluate these asymptotics in that setting. And then, so I had another paper that I mentioned earlier that co-compact unitary groups did some similar moment type asymptotics, eventually resulting in subconvex bounds, but now varying the form of the bigger group rather than the smaller group. And so this boiled down to some relative trace formula analysis where, okay, the symmetry properties were kind of a key ingredient in understanding how to bound the geometric side, and the bound involves some kind of like purely geometric analysis of pictures like this involving how orbits of the parameter tau behave under groups like H, and maybe also some centralizers attached to tau and its projection to H. So this was kind of some linear algebra problem that eventually all this analysis boiled down to, which in the special case here just says that if you rotate the equator, then it intersects itself tangentially, transversely at the point of intersection. So some harder version of this was kind of responsible for these results. Also, if anyone here is interested in kind of formal theorem proving, this is the one result that I've formalized in Lean 4. So just the linear algebra result that this boiled down to at the end of the day. You can find on my GitHub, or you can talk to me if you're interested in that sort of thing. And then finally, we had this third paper establishing kind of bounds for standard L functions using some additional arguments on GLN where things are non-compact, and also where we have to work with Eisenstein series. So there's some analysis of what happens in the cusp. And then I also mentioned this work of myself with Yuki Hu doing kind of analogous things now in level aspects, but where we kind of the novelty is allowing the level to vary in a horizontal manner. So for instance, this prime squared case was a major focus there. And I mentioned that, yeah, there are at least two kind of major open directions. So one is what we might call the fully horizontal case. So an example would be take twisted L functions by Dirichlet characters of prime conductor on say GL4 or GL5 or anything higher than that. That's an open question. And another open situation is what we might call the conductor dropping case, where this uniform growth hypothesis in my theorem 2 fails. So the first of these open directions could conceivably follow from better character sum bounds over finite fields, so kind of much more complicated versions of the sorts of things pictured here that worked, in some cases at least, for GL2 and GL3. So for GL2, this is just an easy application of Weil's bound. For GL3, this is a more involved analysis. So for GL2, or sorry, for GL4, the analogous thing actually involves bilinear sums in character sums that, involve, okay, maybe 6 variables or something like that, depending on how you count, and it kind of goes up and up and up as you go. So the ad hoc techniques that were used, for instance, for GL3 might not be enough, but okay, we'll see. Whereas the second direction doesn't really seem accessible from any of the techniques we've indicated so far in the talk, basically because these techniques are rooted in harmonic analytic arguments using microlocal analysis, where you kind of look at the behavior in terms of, for instance, the parameters defining the representation, and the actual integral representations for which we can make that useful, like GLN plus 1 and GLN. One way to think of it is that they produce moments that are not of high enough degree to counter the smallness of the conductor when some of the parameters are small. So you could look at my third paper, for instance, for kind of a concise description of that difficulty, if you're interested in that. But okay, maybe I don't know that it actually counts as hopeful, but like something that, so my former PhD student, Subhajit Jana, and I have been experimenting with that we hope to kind of get out very soon. I was working on it quite a bit last week, for example, trying to write the paper. So we're trying to develop a way not to understand what happens for GLN and GLN plus 1, but instead GL2n and GLN. So this is just kind of a schematic sketch, but okay, we're taking an Eisenstein series on GL2n, and we're taking its projection. If you know integral representations for rank and Selberg and higher rank, this is the kind of standard projection operator that shows up in that theory. So we take its projection, we restrict it to GLN after translating by some unipotent element that we'll call UQ. So I pictured it here for n equal 2. And so we've basically shown that we can reproduce something like a 4nth moment over all automorphic representations with analytic conductor in some dyadic interval from a representation like this. So in the case n equals 1, this is kind of a well-studied integral going back to a paper of Sarnak in I think 85, and then there's work of Michel and Venkatesh. This was kind of the picture they used for n equal 1 to solve the subconvexity problem for GL1 in full generality. So maybe, because we have such a simple situation here, where we're just translating by a unipotent element, possibly some ideas, like some of these recent advances in homogeneous dynamics, but likely combined with some other kind of genuine automorphic input, might be useful and might shed some light on these sums from the perspective of this integral. But for now, we're just going to kind of be content to actually write down the integral so that hopefully more people can look at this and say some useful things about it. Okay, so with that, yeah, I got some time, but I think I'll just leave this summary slide up, and I'll end now for questions. So thank you.